Okay, welcome to the class, and having discussed DMRS and SRS, we are going to discuss CSI-RS. Okay, we have seen its use, okay, we have seen only its one use. So, we will discuss its another use also, okay, and it will tell us why it is defined the way it is, okay. So, this is our subject of discussion, CSI-RS, channel state information reference signals, okay. And as I said, we have seen one use case of CSI-RS, okay, for a TDD system, okay, where uplink and downlink channel are assumed to be reciprocal, okay. What happened over there was this GNB estimates the uplink channel using SRS. We discussed how it can be done, okay, in all its glory, and then infers the downlink channel from the uplink channel, which is basically the transfers of the uplink channel, right, okay. So, the base station has the downlink channel, it designs the precoder, it sends the precoded signal to the UE so that UE can estimate the MCS, okay, and then feed it back to the G node B, right, okay. So, once G node B has the MCS information, it is ready to transmit the PDSCH to the UE, right. So, this was one use case of this CSI-RS, okay, estimating the MCS, okay. And for what kind of system we did it? It was for a TDD system, okay. Now, there are multiple other use cases of CSI-RS, okay, and just for example, okay, for FDD systems, okay. So, TDD system we have discussed uplink and downlink channel can assume to be reciprocal with the caveat, okay, that like you have to do the TDD calibration, okay. Now, for FDD systems wherein uplink and downlink happen in separate bands, what is FDD? Frequency division duplex, wherein uplink is happening in one frequency band and downlink is happening in another frequency band, which are far separated from each other. Okay. So, uplink and downlink channel are not reciprocal, okay. You cannot infer downlink channel from the uplink, okay. Now, if this is the case, how will base station ever be able to precode, right, okay, and correct, because it does not have the downlink channel information, right. So, then again the CSI-RS role comes into picture, and that is what I am going to show you how it is done, and then we will see how they are defined, okay. So, what happens is in this case, okay, because the G node B does not have the precoder information, what it does is it sends unprecoded CSI-RS for the UE to estimate the downlink channel, okay. I will show you how, okay, because with precoded CSI-RS, UE could only estimate the precoded channel information, okay, and that precoded channel information was compressed channel, right, we saw that H tilde, correct, okay, but that could only happen because base station had the precoder. Now, in this case base station does not even have the precoder, okay, and it needs the channel information from somehow it needs the channel information, okay, to design that precoder. So, what happens in this case is, okay, so G node B will transmit this unprecoded CSI-RS, okay, and I will show you that with this unprecoded CSI-RS, UE can estimate the unprecoded channel, okay, right. So, now if UE has that unprecoded channel, UE designs the precoder and feeds it back to the base station, okay, that will come little later, okay, however that exercise is done, okay. So, the job of precoder design for FDD system is actually shifted to the user, okay. So, user has to design the precoder and somehow feed it back to the base station. We will learn that exercise, okay. But what are we saying here? CSI-RS can also be transmitted as a unprecoded signal, okay, right, okay. So, that is the key, one of the key uses of CSI-RS for FDD systems, and typically just to like make you aware of this fact, because for TDD system, this TDD calibration is kind of difficult task to do, though people know how to do it, but it is a difficult task to do, okay. So, even for TDD systems, people use this CSI-RS, unprecoded CSI-RS, okay, for the user to design the precoder and feed it back. That is also done, Okay, I am telling you now because I have not spoken about unprecoded CSI-RS. Okay, so even for TDD system, CSI-RS is commonly transmitted in an unprecoded manner so that UE estimates the channel, designs the precoder and feeds it back to the base station, which base station uses. Okay, so that this TDD calibration can be avoided. Okay, and that's how it is done in our system also. Okay, so TDD calibration is a non-trivial task. Okay, fine. So now just to like what happened for the precoded CSI-RS. Okay, how was it done? This is done for TDD system MCS calculation. Okay, assuming reciprocity. What happened where in that case, if G node B has NB antennas and UE has 2 NU antennas, what happens? Y is equal to H P tilde plus N. What is P? What was P? It was this. P tilde, it was precoded by using V. Okay, and how did we write it? Now HB becomes H tilde, and what will be the dimension of this H tilde is a NU cross. It was how many ever number of layers you are transmitting. Okay, NU cross NL. Okay, correct. So that's the precoded channel which which UE is estimating. Okay, correct. And how many ports CSI-RS we transmitted? 2 ports CSI-RS. Okay. So this is how we wrote H tilde as W. We are aware of this. Okay, H tilde is basically W lambda V Hermitian V. You are left with W lambda. We have seen this multiple times. Okay, so this is NL cross NL. This is okay, and this is a precoded channel which is NU cross NL. Okay, NL is 2 over here because there is a minimum of NU comma NB. Okay, so now what UE does here is it estimates this and then designs a receiver and then calculates the MCS. We saw that exercise in great detail. Okay, so what G node B does, again to summarize, it transmits CSI-RS for the UE to estimate the precoded H tilde. Okay, and then how does that happen? G node B transmits 2 port orthogonal CSI-RS. Okay, so in this case it is very little. Well, the number of port required is 2. Okay, and it is equal to the number of layers. Okay, and as I said, number of layers doesn't exceed beyond 7 or 8. Okay, correct. So now, okay, so this was the use case for precoded CSI-RS. Okay, so you see that if you look only at this, number of CSI-RS ports should be maximum of 8. Correct, because that's the number. It should be equal to the rank. Okay. Number of orthogonal CSI-RS ports you are going to transmit, if you are going to estimate the precoded channel, it should be equal to the rank. Okay, and rank, as I said, goes up to maximum of 8. That's the kind of channel which user observe. But in the standard, okay, CSI-RS ports are defined up to 32 ports. Okay, there is a key difference. Okay, remember DMRS port, they were also like very limited. SRS port 4, right? Okay. CSI-RS port is 32. Okay, in fact, and if you go for other releases, okay, it has gone, I think, okay, gone beyond 32 also. Okay, I don't remember the number correctly, but it is like defined for more than 32 ports also. And the reason is what? This is the key reason that the CSI-RS are meant for estimating the unprecoded channel also. Okay. Now, if you see the unprecoded channel depends on the number of antennas. There is a precoded channel which depends on the number of layers you are compressing. Look at the dimension of H and look at the dimension of H tilde. What is the this is the unprecoded channel, right? So what is the dimension of this? NR cross NT, right? Okay, correct. And what is the dimension of this? NR cross NL. This is if the base station has 32 antennas, what will be the dimension of this? 2 cross 32, right? Okay. And what is the dimension of this? It is for if NL is 2, it will be 2 cross 2, right? Okay. Now CSI-RS is, as I said, is used for estimating the unprecoded channel also. For FDD system, I gave you an example, right? Okay, correct. And if the unprecoded channel has to be estimated, you have to design based on the dimension of H, not H tilde. Okay, so you see this, that how many, and the way this 5G networks are being designed, we are talking about massive MIMO base stations wherein the number of antennas are very large. Okay, let's say to keep things simple, it is basically H is, if the base station has 32 antennas, you need 32 port CSI-RS, and that's how CSI-RS ports have higher number of orthogonal ports. Okay, so what is this? This is unprecoded CSI-RS transmission. Y is equal to HP plus N. What is the dimension of P? If H has, base station has 32 antennas and NU is 2, it will be 2 cross 32. You need 32 port, right? Okay, so base station has to transmit a 32 port CSI-RS, and look at the overhead, right? Okay, correct, when compared with the 2 port CSI-RS. That's why TDD is actually preferred, that you can reduce this overhead. Now you can understand, okay, that if it is an unprecoded channel, it has a high CSI-RS overhead for its estimation when compared with a precoded channel. Okay, and this is typically, according to theory, it is required only for FDD. Okay, for TDD you can use the reciprocity. Okay, so in general, if you are able to exploit the reciprocity, the CSI-RS now we know is much lesser for a TDD system when compared with the FDD system. Okay, so what happens for a FDD system? Okay, base station is sending this unprecoded CSI-RS, and user has to estimate this unprecoded channel from here. It can, okay, because if you send a 32 port CSI-RS, we know how to estimate H from that. Okay, so UE estimates H and then designs a receiver to calculate the MCS. Okay, right, and it calculates something called channel rank. It calculates precoder matrix information. We'll discuss later. Okay, as I said, because only UE has the channel information now. Base station doesn't have, right? Okay, then who is going to design the precoder? As I said, UE is going to design the precoder. So that information goes as PMI information, precoder matrix information. Okay, that is also part of the UCI. That has to go back. Look at the overhead, right? The precoder has to go back to the base station using control channel, and that control channel is UCI. Right, and it has to tell what is the rank of the channel also, okay, because only user has the information. Okay, so all this we'll learn how this is done. I'll give you a recipe to do that later. Okay, but that's the need of transmitting an unprecoded channel or unprecoded CSI-RS so that H can be estimated. Okay, and that's why it is number of port is very large for CSI-RS. Okay, so GNB will transmit to estimate NU cross NL, GNB will transmit not NB, it is NL, okay, port orthogonal CSI-RS, right? There is a typo over here. So what I am saying, if I am assuming it to be NU cross NL, okay, if it is NU cross NT, you will have to transmit NT port CSI-RS, okay, correct? So this is what the key background of CSI-RS. Okay, it is used for estimating unprecoded channel also. Okay, now as I said, it is defined for a maximum of 32 antenna ports. Okay, unlike SRS and CSI and DMRS. Okay, DMRS we remember maximum of 8 ports. SRS 4 ports, and this is 32 ports. Okay, so I'll show you how it is defined for a single antenna port. To estimate a single antenna port, it is only one resource element per per PRB is transmitted. Okay, this is one port CSI-RS. That's all. Okay, as I said, if it is one port, how many resource element you need to estimate the channel? It is only one, right? Okay, so we are assuming that the channel remain constant over the entire PRB. Okay, correct. So single port CSI-RS occupies a single resource element in a RB in one slot. Fine, okay, and the CSI-RS can be configured to occur anywhere within this RB. So you can configure this so that it comes anywhere in this resource block, and that configuration will be told to the user. Okay, so user will basically use this and then estimate the channel and then do its desired processing after that. Okay, and what channel it is estimating? It is estimating the unprecoded channel, right? Okay, fine. So, and you look at this, what is the density of the CSI-RS over here? Okay, so the density here is one resource element per antenna port per PRP. What does that mean? Okay, so how many antenna port this CSI-RS has? It has only one antenna port, correct? Okay, and how many resource element, how many such CSI-RS you are sending per PRB? You are sending only one per PRB. And how many REs you are using? One RE, right? You are using one RE per PRB. And how many antenna ports it can be used for? It can be used for one antenna port. So this is called the CSI-RS density, okay, right? And we'll see that this is one example, okay. You can increase the density also, okay, which essentially means that I can transmit even for, if I say it is 3 RE per antenna port per PRB, what does that mean? Okay, I can configure this CSI-RS to come here and to come here. Or I can configure it to come here, come here, come here, anywhere in this PRB. That's what it means, right? Okay. So typically this is the technical jargon used for CSI-RS. How many REs per antenna port per PRB you are transmitting? Okay. So if the channel is varying over the PRB, what will you say? Okay, you will tell that it is basically, you will use higher density CSI-RS. If the channel is constant over a PRB, you will use a lower density CSI-RS, right? And what is the lowest density you can use? Okay, this is 1. Okay, I can use it, I'll show you example. Okay, I can use it 0.5 also. Just for example, if it is, I send only one CSI-RS per 2 PRB, then what happens? The density further reduces, right? Okay, so it will become 0.5 RE per antenna port per PRB. Because if you extend this, okay, right, and don't send a CSI-RS in the second PRB, and you count the density over 2 PRBs, okay, and then you send it over third one, correct? So the density of PRB of the CSI-RS has become half when compared with 1 RE. I'm just giving an example how it can be configured. Okay, right? So this is an example for a single port CSI-RS, right? Okay. Now if you have to go to 2 ports, that's what we are going to show. Okay, so that's, look at, so one has to understand this, that they are defined for up to 32 ports. Okay, so you have to create such structures which are scalable. Okay, 1, 2, 4, 8, 16, 32. Right? Okay, correct. So we are moving in steps wherein I am showing you CSI-RS for 1 port, I am showing you how it is extended for 2 port CSI-RS. We'll go to the next lecture and I will show you how it is extended for 8 port, 16 port. Okay, so what is happening here? What are we showing here? This multiple orthogonal CSI-RS ports are designed using code division multiplexing, frequency division multiplexing, and time division multiplexing. Okay. Right? We have seen the example. For DMRS, we have seen it, how that FDM, TDM are used and CDM are used. Okay? We'll see it over here. So look at this. This is the most common example we have been using. Right? What is the first port? What is the code for first port? +1 and +1 -1. So this is, if you look at it from understanding the concept of port, how many resource elements we are using? We are using only 2 resource elements to construct CSI-RS for 2 ports. Right? Okay? So what happens here? So this is what we are doing. We are taking 2 resource elements, and then in this code domain, what happens? Different antenna ports CSI-RS are transmitted on the same REs, correct? Okay. You look at this, first port is being transmitted on this and this RE. Second port is also being transmitted on this and this RE. That's the statement I am making. Okay. Right. So different antenna ports CSI-RS are transmitted on the same REs. Okay. This is for, we are using to transmit 2 port CSI-RS, we are using 2 REs. Okay, right? And so orthogonality among the ports is achieved using different orthogonal codes. In this, that's what we have done. Okay, so you are using 2 REs and you are using codes, 2 length code to create orthogonality among 2 port. Okay, and this need not be done. We have taken another example in the beginning, where if this becomes 1 0 and this becomes 0 1, for port, let's say for 1 port it becomes 1 and 0, for second port it becomes, this becomes 1 and this becomes 0, right? Okay, what is that? That's not CDM, that's FDM, right? Okay, because you are achieving orthogonality using by using different REs, correct? So I am just bringing out that aspect over here, okay, that it could be done using FDM also, but you don't do that, you don't use 1 0 and 0 1. We understand, because the transmit power reduces, correct? Okay, so this is why this orthogonality among port is achieved using different orthogonal ports or different orthogonal codes. Okay, so you are using 2 resource elements for each port, okay, right? But on an average, how many resource elements you are using per port? Only 1. Okay, so this is code division. Okay, frequency division. I'll show you the example. Different antenna ports are transmitted on different REs. Okay, we'll look at that also. Okay, then time domain. Different antenna ports CSI-RS are transmitted on different OFDM symbols. We'll look at that example also. Okay, right. So orthogonality among ports in FDM and TDM mode is achieved by using orthogonality across resource elements and OFDM symbols. Here you will use different resource elements, okay, in frequency to create orthogonality amongst different ports. Here you will use resource element across OFDM symbols to create orthogonality across different ports. Okay, right. What is this? What do you call this? So above 2 port CSI-RS is an example of 2 cross this CDM, right? Okay, what is happening? You are using, so how are you separating these 2 ports, W0, W1? Okay, this is the code. Okay, both the ports are using the same REs, so they are not distinguished using FDM, right? Okay, how are they distinguished? They are distinguished using CDM. And what are we calling 2 CDM? Because you are using length 2 CDM to distinguish these 2 ports. Okay, so what is happening here? Again, you look at this. What is the density? Do you agree with me that this CSI-RS, even for here in this case, what is the CSI-RS density? CSI-RS has a density of 1 RE per antenna port per PRP. How many antenna ports CSI-RS we are sending? 2. How many resource element we are using? 2 in a PRP, right? So 2 by 2 you get 1 resource element per port, and this is happening, entire operation is happening in a PRP. So you get 1 resource element per antenna port per PRP. Okay, so we saw the example of 2 port CSI-RS, and we are going to see example of 8 port CSI-RS, how it is constructed using different FDM, CDM and TDMs. Okay, so you look at this. I have taken 3 different examples here. Okay, we'll look at them one by one, and this bullet is telling this 8 port CSI-RS are created using CDM oblique FDM oblique TDM in multiple different ways. Okay, right. So first example is a 2 cross CDM combined with 4 FDM. What are we saying over here? Okay, look at this. Why am I saying CDM? Okay, look at this 2 CDM. Okay, this is 2 port. I'll use 2 port code, 2 length CDM over here. I'll be able to create 2 port CSI-RS like I created in the last slide. Right? I used how many resource elements I used? I used only 2 resource elements, and I created 2 ports. So I'll create using this red resource elements are going to give me 2 port CSI-RS. Okay, right? But what about the rest of the 4 ports? How am I creating? I'm using this same code, and then I'm using frequency division multiplexing. How is this frequency division multiplexing? This coming over here, they are not interfere with each other. This is another 2 port, this is another 2 port, this is another 2 port. Right? So that's how you should read it. 2 cross CDM plus 4 cross FDM. Okay, total of 8 ports. Right? Okay, that's the terminology which is used in the standard. So you should get used to it. Nothing like the fundamentals are very simple. You need to create an 8 port reference signal, you need at least 8 resource elements. How do you create them? Left to you, or left to the standard. Okay, you either can do it across frequency, you can do it across time. That's what we are seeing now. Okay, right? So terminology can get confusing, but that's what is happening. Okay, right? So first example is 2 cross CDM combined with 4 cross FDM. Okay, why 4 FDM? I just said that they are replicated across another set of resource elements in frequency. Right? That's why FDM, no TDM. Okay, look at second example, 2 CDM, 2 FDM and 2 TDM. What is happening? 2 CDM, what is this? 2 FDM, and then is replicated across time, so you are calling it 2 TDM. Is this clear? Okay, right. So, third example, 4 CDM combined with 2 FDM. Okay. So, what is this? What am I calling over here? Okay, here look at this. These 4 resource elements in red, okay, that is the color coding. Whatever the same color is being differentiated using codes. Okay, right. So, this is red, so you are creating 4 different ports using 4 codes, okay, and then you are replicating them across frequency. And why are you not calling it TDM? Because the baseline itself, you are using this 4 CDM, and which is spread across time itself. Okay, so you are not using separately the time axis to orthogonalize the port. Okay, so this you can argue that here itself, okay, 4 ports are using FDM here, TDM. That's not how it is defined in the standard. Okay, right? These 4 ports are differentiated using CDM. Okay, and these another set of 4 ports, they are differentiated using FDM, because you are not differentiating them like this. You are differentiating by extending over frequency axis. Okay, where you are extending, that's what this dimension is. Correct? Okay, here you see 2 CDM, you are extending them over frequency, so you are calling 2 FDM. And then both of them you are extending over time, you are calling it that as 2 TDM. Doubling. Okay, right? That's the terminology. Okay. So again, above CSI-RS has a density of, how much density the CSI-RS has? 8 ports, 8 resource element and a PRB. So 1 resource element per antenna port per PRB. Right? Okay. So that's how we have studied up to 8 ports, how CSI-RS are generated in the standard. You can see it for yourself how 16 and 32 are generated. So we'll not go into the details of that. I'll stop here. We'll continue discussing this in the next class also. Okay. Thank you.